President put it in the morning. Suppose we all know what this session is all about, and basically what we try to do here is to emphasize the use of spectroscopic techniques and kinetics to study reaction pathways and characterize catalysts. It wasn't my idea of having the session on Friday. I assure you that in the next 4 years at least we'll go back to our usual format on Tuesdays or Wednesdays. As I am the co-chairman of the Area 1B now. I'd like to invite some of you to get involved in programming these sessions so that I'm not the only one blamed for the wrong timing and so on that is assigned to the session. Originally I submitted 20 minutes for each speaker, and if you look at the program, Nick Delgas is going to have to rush up because his talk is scheduled for 5 minutes. So, but I'm not going to be fussy about the time, try not to go over 15 minutes anyway. This organization here in Washington is very special. It doesn't happen this way in other meetings. Finally, the title of the last paper has been changed. It's Monte Carlo simulations and FTIR studies during C oxidation on platinum. Another note is that the talks are going to be video here, and you please sign a release or something agreeing to that purpose that we have up front the speakers, please. So, without other comments, I would like to introduce our first speaker. The title of the paper is The Effect of Preparation Method and the Extent of Reduction on the Apparent Structure Sensitivity of Iron CO hydrogenation catalyst. And this is work co-authored by Calvin Bartholomew and Ramaswaran, who is now at Michigan State University, and he will be presenting the paper.
Just found out that we only have 15 minutes, so let's try to move this paper along as fast as I can. And this work was done at Brigham Young University under the guidance of Professor Bartholomew, and he's unfortunately couldn't be here today, and he has asked me to present the paper. For a reaction to be classified as a structure-sensitive reaction, according to Buddha, this reaction has to be confirmed to be structure-sensitive on single crystals as well as polycrystalline supported catalyst. The CO hydrogenation reaction has been eluding such classification, as we can see in this slide. On single crystals of various metals, this catalyst was found to be structure insensitive, whereas on supported catalyst, depending on the metal, the specific activity increased by a factor of 2 to 1,000 fold, depending on the metal. Why is the supported catalyst eluding this classification? One, the structure sensitivity itself could be due to a primary effect of structure, or it could be due to any of the 3 secondary effects as shown here, the decoration by support moieties, chemical contaminants such as carbon, chlorine, and sulfur probably would be involved in contaminating the crystallite, and thus inducing a secondary effect of structure sensitivity. And finally, the modification by metal oxides, such as difference in the extent of reduction, could be causing such apparent structure sensitivity. But if it was the primary effect, then we would have observed that on single crystals also. The secondary effects, such as decoration, could be avoided if we investigate this catalyst on supports that are not reducible, such as the titanium oxide and vanadium oxides are known to migrate onto the surface of the crystallites, and thus thus modifying the crystallite surface and inducing a secondary effect. But if we use a support such as alumina, we might be able to avoid this problem. So our studies indicated that even on alumina supported catalyst with conventional preparation, that is, for example, here catalyst prepared by impregnating a nitrate salt of iron, we find that upon drying this aqueous impregnated material, we form hot acidic solutions form in the nearest proximity of the alumina surface, which etches some of the alumina and dopes the metal oxide layer. And upon reduction, we end up having crystallites that are decorated with these doped aluminum oxides. And one could envision that the extent of this decoration could vary with varying crystallite size. And this phenomena has been observed as early as 1974 at Ford Motor Company, and has been documented, observed, and postulated and documented for cobalt nitrate prepared catalysts. And many other workers have observed similar decorations for this of these crystallites. And our TPD experiments in Moscow indicate that these crystallites are probably decorated. So one way to avoid this decoration is to prepare the catalyst by the decomposition of metal carbonates. This has two advantages: that we avoid any other chemical contaminant that might be arising from inorganic salts, in which in this case, we impregnate the alumina, the well-dehydroxylated alumina, with iron pentacarbonyl in a pentane solution. And the carbonyls attach themselves to the surface hydroxyl groups or the coordinatively unsaturated defect sites in the alumina surface itself. And upon reduction, we end up getting fairly well reduced and well dispersed metal crystallites. And these crystallites, as I said, are probably not decorated, and we have evidence from Moscow Spectra that they are not perturbed by the other contaminants. Therefore, for this portion of the study, we formulated this objective, that is to investigate the crystallite size, conductivity, and selectivity properties of CO hydrogenation catalysts in the absence of decoration and iron oxide modifications and chemical contaminants. The decoration and chemical contaminants could be avoided by preparing the catalyst, as I said, using carbonyl. But we were unable to eliminate the extent of reduction and yet get variations in dispersion. So we thought we'll use that to our advantage and hold that constant. So to do that, we prepared the catalyst, we prepared two sets of catalysts. One, by holding the extent of reduction constant by varying the weight loading on a support that was dehydroxylated at a constant temperature of 650 degrees centigrade. And the second way is to vary the extent of reduction also along with the dispersion. This was achieved by having the weight loading constant and varying the support dehydroxylation temperature. In order to get a good reduction temperature for this purpose, we reduced the iron pentacarbonyl impregnated catalyst, and this is for a 4.5% iron alumina catalyst prepared on a support that was dehydroxylated at 650 degrees centigrade. We find as the reduction temperature increases, the extent of the dispersion goes through a maximum of close to about 30% of this catalyst, and the extent of reduction essentially goes to 100%. Higher reduction temperature rendered this catalyst to be poorly dispersed. Therefore, in all our studies, we used, especially the iron catalyst, we used 300 degrees centigrade as our reduction temperature. Now, in this slide here, I'm presenting the effects of weight loading on the physical properties of this catalyst. this first set of catalysts where I had varied the weight loading, and we obtained a widespread of dispersion, and the extent of reduction was held constant around 55%. Now, on the second set of catalysts, where I held the weight loading constant at 4.5% and varying the support dehydroxylation temperature, we find the dispersion decreases while the extent of reduction increases with increasing support dehydroxylation temperature. Now, for the first catalyst, I was unable to obtain a significant oxygen titration value to calculate the extent of reduction. Therefore, this was obtained from curve fitting the Moskwa spectra. But the hydrogen uptake, together with some of the extension, together with the value that I obtained from Moskwa spectra, gave us a dispersion of anywhere on the 50 to 100%. But the trend of decreasing dispersion with increasing support dehydroxylation is evident in the slide. Now, these are the Moskwa spectra for these three catalysts that I showed in the previous slide. The first one is for the catalyst prepared on support dehydroxylated at 200 degrees centigrade. This one 650. And the third is for the one that was dehydroxylated at 800 degrees centigrade. And this is a pure iron foil that we use to standardize our spectrometer. And these are the curve fit parameters for these catalysts. And as you can see, that the iron 0, which is only about 5% of the area of the first spectra, indicate that this is iron present here are superparamagnetic. The iron 0 here are magnetically split, and so are the iron 0 in these two cases. The parameters such as the isomer shift and the hyperfine field indicate that these metals are almost identical to the pure iron foil. Now let's look at the activity and selectivity data for these catalysts. As the dispersion increased while holding the extent of reduction fairly constant, the turnover frequency remained almost the same. And the hydrocarbon selectivity also remained the same. And if you look at the individual product selectivity, there was nothing, this too remained fairly constant. This is contrary to the observation for supported metal catalysts, where you find a wide variety of changes in activity and selectivity properties with changing dispersion. Now, on a typical plot of structure sensitivity, you find if we look at it this way, we would conclude that the CO hydrogenation on this set of catalysts is probably structure insensitive. But now, when we look at the second set of catalysts, where the dispersion was varied, which was also accompanied by the variation in extent of reduction, we find an order of magnitude increase in activity with decreasing dispersion. And hydrocarbon selectivity has increased with decreasing dispersion. And the selectivities, you have lower selectivity for higher hydrocarbons on poorly dispersed catalysts. Sorry, the higher selectivity for higher hydrocarbons on poorly dispersed catalysts, and vice versa for the poorly dispersed catalysts. These are the typical observations for structure sensitivity on supported metal catalysts. Now, if we plot again on a structure sensitivity type of plot, as we call it, we find an order of magnitude change in activity with change in dispersion. If we happen to study the catalyst under these conditions here, we would also conclude that the CO hydrogenation on iron would happen to be a structure sensitive reaction. So we wanted to see if anyone else has observed similar trends, and we went into the literature to see the other data, if they have any information on the extent of reduction. And we find there were only two other data for supported iron catalysts which indicated the extent of reduction. One was that done at our own lab, and the other one was Storm and Budash's work. And we find that as the reduction increases, like here, the turnover frequency also increased by an order of magnitude. From these we could come to the following conclusion, saying that CO hydrogenation reaction on iron alumina is probably structurally insensitive. And the presence of metal oxides, either in the form of alumina or unreduced metal oxides such as iron oxide, in the immediate vicinity may influence the activity and selectivity properties of iron alumina to a greater extent than the structure itself. I would like to acknowledge the following for financial support. Thank you.
Questions?
Could you comment on what the evidence is for the alumina decoration of gold? You talked about the problem in those catalysts. How do you know that the alumina is on top of iron? How do you know that the alumina is on top of the iron?
Well, we, from electron microscopy and as well as chemisorption results, we find that crystallite size are dispersed to be about 30 to 40% dispersion. And on a TPD comparison of this alumina, the conventionally prepared catalyst against a carbonyl-derived catalyst of similar dispersion and weight loading, indicate there's a shift in CO desorption speed, and that indicates to us that there is a chemical interaction, which is different from what Mark here has done. They found that there was no chemical interaction, but ours agrees well with that of Jim Domestic at Wisconsin. Keep on decoration to affect the absorption.
I have a question about your technique. When you do this percent reduction by oxygen,
Right.
can you then reduce the catalyst again and get the...
No. On alumina catalyst, when we cook it at 400 degrees centigrade, we get into an iron aluminate or a form that is not easily reduced back reduced back to iron zero. So, but we were able to do that with ruthenium or other noble metal catalysts. The reduction is possible, but not with the base metal catalyst. Thank you.